The thing that I've done at the beginning of the seminar series for the last several years is to give a non-technical talk, and as you've probably gathered from the title for today's talk, today is also a non-technical talk. And so here, today we'll talk about the secrets of memorably bad presentations. After I shared this by email, one of my colleagues this morning said, "David, you're exactly the right person to give this talk," which I thought that was a little unkind, but you know, what I'm going to do throughout the talk is I want to structure this as an actual technical talk, as you might see at a conference. So for instance, in about a week or so, I'll be going to a conference in California that's called MOF 2016. There's going to be 500 people there, all giving talks about metal organic frameworks. And what I want you to imagine is that I'm giving a talk at that conference for about 20 minutes, and I'm going to deliberately illustrate some very bad habits. Okay, so please don't give a talk the way that I'm going to do it today. But I'm going to deliberately just show you some ways to aggravate and torture your audience. So one of the things that we'll do as we go through the talk is I'll try and highlight some of those things as we do them. What I'm going to try and do, we have some special refreshments set up, and so in the sense of keeping it just like a conference talk, there's a time when you're supposed to end, and so my objective will be to finish by about 4:25 or 4:30 on the clock over there, and then we'll be able to enjoy some refreshments outside. So let's go on with the show. Oh, okay, already have a problem. I can see that, let's see what I've done here. Oh, okay, I see what I've done. I've got the wrong slides open. So let's go with this one. All right, great. So now we're ready to start. All right, so you can see that I just managed to kill about 1 minute of my 20 minutes by fiddling with my computer. Very, very bad idea. There's almost no excuse for it. Now, in fact, just so that you know, I did actually come in this morning and verify that everything would work in this room. Okay, but there's your first thing not to do, is don't hassle around with technical difficulties. So there are new faculty. What I'll do as we go through the talk is to highlight these tips for you if you want to take notes. So there's my first one, to waste time with technical difficulties. Now, it does remind me, though, this conference I'm going to next week is a very, very international conference. And so it reminds me of last time I was at this conference. One night, a number of us decided to go out for dinner. And so we were able to get together a large group of people. And in fact, we had 2 Americans, a Canadian, someone from Britain, a Malaysian, someone from China, and then finally we were joined by someone from Bulgaria, so a Bulgarian. So we took this group out and we walked down the place where this conference was to try and find somewhere to go to dinner. And we finally found somewhere we wanted to go to dinner, asked for a table, and the maitre d' told us very politely, "I'm sorry, we can't let you in, you don't have a tie." Okay, so that was a bad joke, right? So the idea is that I've just wasted your time with a totally irrelevant anecdote. And in fact, I even managed to do it in a way that you didn't even know it was a joke, right? So that's a really bad joke, right? When you can't tell that there's a joke going on. So there's your second tip. All right, so now let's get to the actual part of the introduction. I'm at a conference. As I said, there's going to be literally hundreds of talks at this conference about metal organic frameworks and about how they're used in ways that could potentially save energy. And probably I'm talking in a session where we've just had 5 talks in a row all about using these materials in energy applications. But this is then a way that you might want to begin by really backing up to the dawn of time, right? So you realize that really from the dawn of time, people realized that having energy is a good thing. And so here's a picture of our ancestors. They decided that having energy was a good thing. And eventually, as time progressed, we got to the Industrial Revolution. And that was great, right? People's standard of living started to rise. We automated manufacturing. We had transportation around the country and all kinds of good things. And so now if we think about the implication of that as we move into modern society, one of the things we've realized, of course, is that by burning stuff, we're putting carbon dioxide into the atmosphere. And so maybe that's not such a good thing. And so you know that one of the outcomes of burning fossil fuels and putting CO2 into the atmosphere is causing global warming. Global warming is clearly a bad thing. It makes animals sad. Okay, so this, I mean, this guy's really not having a good time. But it gets worse than that. I mean, it makes puppies sad. It makes little children sad. It makes grown men angry. All right, so hopefully this is amusing, but it has nothing to do with the technical talk I'm going to give, right? And so this is my sort of tip to you as you give these talks, that think about who your audience is, but then think about the most patronizing possible introduction you could give, and that's a great way to start with your presentation. Okay, so now let's move on to a real introduction to the talk. And so I'm probably going to be talking about work from my research group, where we work on modeling of absorption and diffusion in nanoporous materials. Now, one of the things that's known about these materials is that zeolites, among other materials, have been used in industry for a long time. And in fact, they definitely are used on very, very large scales. So there's a lot of interest in understanding how these materials work. And over the past 20 years or so, there's a large literature that's been developed looking at modeling of these materials. And in fact, groups all over the world have worked on this, right? And so there's now a very, very large literature on these materials. And in fact, one of the advantages of modeling is that the modeling has now reached the point where it's more precise than experiments. All right, so you get my point here, right? Which is, I've been somewhat selective in looking at the literature. So my tip here is, when possible, completely ignore the contributions of others, okay? That's a really good way to get your audience on your side, especially when they're the people that have done some of the work, right? Now, the other more serious point I'll make here is that I've deliberately obscured the name of every single person who's ever worked with me on this slide. In general, that's a very bad idea. For this talk, it's actually important because I want to make it clear that although I've abstracted their work, all the slides are my fault, okay? So all the bad habits that I'm trying to show you here do actually come from my own estimates of trying to make this bad work. All right, so I've given you some introduction to what the topic of my technical talk will be about, but then it's typically what people like to do is include a slide where they give you some sense of how the talk is going to go. And so we'll start with an introduction. Well, I've already done that. But then we'll get into some background. But before we talk about the results, I'll have to tell you about my methods, right? But after the methods, we'll have some results. Then that will lead into some discussion. And then finally, I'll end with a conclusion. This is terrible, right? But you see slides like this all the time. There's nothing on this slide that gives you any information at all. I mean, hopefully I'm going to end with a conclusion, right? And hopefully I'm going to begin with an introduction. So please don't make slides like this. So here's my tip. Use an information-free outline, right? If you really, really have to have an outline, have some good reason for doing it. One way to think about this is if you go to a music concert, people don't stand up and say, I'm going to sing a song now, and it has an introduction, and then a verse, and then a chorus, and then a bridge, then a chorus. I mean, they don't do that, right? They just sing the song. And so that's hopefully what you can do with your own talk as well. All right, well, so far we've talked about the introduction part of giving a talk. One of the things that often happens when you have prepared carefully to give a talk is that when you finally get in front of the room, that you get a little bit nervous. And often when you get a little bit nervous, there's a bit of a shot of adrenaline. And that, you know, one of the side effects of adrenaline is it often makes people talk a little bit too quickly. And so if you're ever tempted to talk a little bit too quickly when you're giving a talk, I would like you to think of this guy. See if I can get this working.
So let's get the auction underway. On the first count here, we've got 55. 55, 59, 50, 1, 2, I think 30, 30, take the more, take the more now, 84, 55, 55, bottom half, 55, now quarter, 55, 75, 75, 65 and a half, 21, and you rock, 21, rock star, 21.
All right, so there's multiple things that's great about this video. First, I mean, you got to love the guy's hat, right? And then you notice there's a guy sitting next to him with the same kind of hat on, right? So if you ever think that people from Canada are a little bit too mild, this is from Saskatchewan, right? So it shows you. Now, I know you want to see it again, so we'll watch it one more time. But again, I want you to just imagine actually seeing someone give a talk like this.
The first count here. Who's got 55? 55. 65 and a half. 21. 21, Rockstar, 21.
All right, so don't talk too fast. So now that you've made it past the introduction, hopefully you've calmed down enough to give the talk. It's time to get into the actual technical meat of the material. And so let's look at how we would often present the technical material that we've got within the talk. And so as a first slide, you might have something that looks like this that starts to describe some of the results that you have here. And so what we've got here is a picture of one of these metal organic frameworks that we're looking at. We've been simulating adsorption isotherms, and there's also some experimental data in here. And I've got a number of details here about how we went about doing these calculations. Now this is a terrible slide, okay? There's multiple things that are wrong with it, but one of the things that, and this is actually a subtle thing, but it's a good way to kind of torture your audience, is to use as many fonts as you possibly can on the slide. So I think I came up to 7 before I had to stop because I was feeling ill. But so the first tip there is use as many fonts as you possibly can. The other thing is if you start to look at this in a little bit of detail, even for the folks that are in my group, and I'm looking at a couple of them here, they're having trouble to decode what this slide is because I've crammed so much jargon and information onto it that it's hard to know what's going on. And so there's your tip if you want to give a terrible talk. Just don't hold back at all with the acronyms and jargon. I want to particularly highlight this last little bit that the sort of a Star Trek homage there doesn't mean anything at all, but it just made it up to sound like it was a very technical approach to what we're doing. So let's hope that we've made it past this slide and you've learned something about what we're trying to do with these simulations. Then it's time to actually show you results from the calculations. And of course, a typical way to show the results is to show a table of data like this. Now this is a very, very informative table because one of the things we decided to do was to look at a range of different materials, and in particular we wanted to look at a whole range of different space groups, right? And so you can see in particular that as well as looking at the CM-CM space group, we wanted to include 141/AMD and 14/MMM. As you all know, that's really important to include all of those different things. So we looked at the lattice constants for these particular materials, and then we started to compare experiments and calculations. And what you can very, very clearly see from this table is that there's good agreement between the experiments and the calculations. You just have to look, you know, here's the data for the experiments and the calculations. Now, you can delve into this a little bit more deeply if we look at, you know, one more set of the data here. And so what we're looking at here is information that really tells its own story. I don't need to explain it to you, but especially I want to highlight a couple of these things. And, you know, really this is an incredibly surprising result, and I think you'll all straight away know what the message is here. So this is a very nice way to represent the data. Now, of course, the message here is smaller fonts and denser tables are always better, right? It's always, the more stuff you can possibly put onto the slide, the better off you're going to do with communicating it to your audience. Now, you've probably heard the advice, though, that, well, it's not so good to show all this information, but you would like to be able to show things in terms of a picture. So the other point that I need to make before I go to the next slide is, notice that I haven't troubled you here with any words on the slide. Okay, so maybe I had some point that I was trying to make, but I didn't actually take the time to fill in any of this space here because apparently it's self-evident what you're supposed to learn from the slides. So don't waste space on the slides by putting in words and things like that. Now, one way to avoid all those tables, of course, is to actually just show some experimental data. And so that's what I'm showing here. We've done work where we've collaborated with folks who are doing neutron scattering. And again, the wonderful thing about this data is it really is self-explanatory. right? And so you do this initial experiment, then by expanding this region here and looking at a different energy range, you can start to see some slight asymmetry in the data here. That's just instrumental noise, so you can ignore that. But by the time you start to go down to this energy range, the features really start to come out, and finally, at this highest level of resolution, this very slight shift in the peaks here is really telling the whole story of this data. Now, one of the ways that people like to analyze this data, the problem here is it's being plotted in terms of momentum transfer. It's much better if you replot the same data by looking at different vectors spanning the Brion zone. So that's what we're showing here. We're comparing some DFT results with the results of these experiments. And again, I think you'll agree that the story is very, very clear, that you don't need words on the slide to explain what's going on. Now, in fact, these are examples that I took from the literature. There's even better you can do. So this was a very nice figure that I found that describes similar kinds of experiments. That's what it's comparing here is some scattering data and then various analyses of these things. And in particular, I want you to address your attention to this part J of the figure, where you can see that there's a slight feature here that really is very important in understanding these materials at all. All right, so what am I doing here? Picture is worth 1,000 words, so just use pictures, right? Well, so clearly if you're going to show data like this, it's the same as showing some kind of dense table. You need to write down what's going on. But I did another thing here that I think is a little bit more subtle and is really a good way to sort of make your audience uncomfortable, and that is I've managed to show a huge amount of data that I didn't mention at all, right? And so if you look at this figure, this is really a work of art. This doesn't come from anyone at Georgia Tech. This has parts A through Q on the same figure, which, I mean, that's really quite impressive, I think. But I was very careful to only describe one panel in that whole thing and ignore all the rest of it. Now, if you're giving a talk, you should prepare ahead of time. Just have the data that you actually want to talk about. All right, so as I said, we're going to give about a 20-minute talk, and probably at about 4:30 we'll be wrapping up. So at this point, I'm looking over at the clock and I'm realizing that I'm actually running a bit short on time. And so now I have a bunch of slides here to illustrate a point, but I think I'll just have to skip through a few of them. So let me just click through these so we don't waste time. All right, so you've already figured out what I'm doing, which is skip a whole bunch of slides in your talk. These days, if you're giving a talk, you know how long the talk is. You should have prepared. In order for you to have the right set of slides on your computer, it's the work of minutes to do that, right? And so there's really not an excuse for including these extraneous slides. Unfortunately, I have to point out that I actually have a few more extraneous slides, so I'm just going to have to click through those as well. Actually, this really isn't so much part of the story that I wanted to tell, but it's such wonderful data that I have to say a few words about it. So this is work that we did on metal hydrides a number of years ago, and it illustrates the idea of predicting structures ahead of time with the computer that we can't immediately identify in experimental data. And so if you look at this, we have prototype structures. The transition metal in these complex transition metal hydrides is identified, as is the cation. And if we look at these examples, what's shown in green are examples where experimental data is known, and these white samples are cases where there's no experimental data. Think about how cation ordering works in these material, and it seems very, very likely that, in fact, we should be able to fill in this white space here. As I said, this talk's not really about these metal hydrides, but this is a nice example of some of the computational approaches that we've used in doing this kind of work. All right, so my tip here, this is for the real experts. You want to skip over the slides, but then actually talk about them anyway, right? So this is actually a pretty common technique, very, very aggravating. But that's a good one to, especially if you have extra material that you need to be able to slide into the talk somehow. All right, so a couple more slides here that I have to skip. Sorry about that. And finally, we start to move towards the end of the talk. So I have my conclusions. And I have what I have to say is a fairly ugly conclusion slide here. I've just taken my long, wordy captions from the figures in the paper, and I've just copied that directly onto the slides. I've also just copied the figures directly onto it. It's a little bit difficult to tell by looking at the slides what really my point is, but the main point is that, in fact, we can see very good agreement between experimentally measured isotherms and the predictions of our calculations, and that we can use that then to look at a whole range of different materials. So that's a nice place to conclude the talk. At least you would be led to think so by the slide. I've done a couple of things here to mess with your mind a little bit, though. I'm not sure if you noticed the slide number here. So once in a while you'll see a talk where someone has slide numbers that really seem mainly designed to put doubt into your mind. And so here I've used slide numbers to inject considerable uncertainty in your mind about when it is that I'm actually going to stop talking. And that will be further magnified when we go to the next slide. What follows the conclusions, of course, is a slide about our continuing work. And so now we move on to the second part of the talk. We've been motivated by the results in the first part of the talk to look at some of the internal structures of these materials. And so this has motivated us to look at a range of these structures with microscopy. And we've recently actually made some of these structures. We have very, very small amounts of these samples experimentally. But nonetheless, by analyzing them, we know we have the correct materials. All right, so my tip here is that if you can put a false ending into your talk, that's always great, right? You let people think that you're finishing and then just charge straight ahead and make sure that you're going to talk about something completely different. That's really a good way to get people on side. Now, a typical thing that happens when you're showing this kind of preliminary data is you realize that, you know, we've got a partial story here in particular. We have synthesized these materials. We have very, very small samples. And so we needed to do some characterization to understand what these materials are. And so here's some data actually that one of the students in my group emailed me last night. This was an experiment that was done yesterday. We really haven't analyzed it at all, but I wanted to show it to you because I think it starts to explain what's going on. And you can see from this mass spec data that we have a lot of different peaks, and so we're starting to understand what these materials are. All right, I've done a couple of things on this slide. Notice actually my slide numbers have gone backwards, right? So now I'm really trying to mess with you. But the other thing is that I've made a point of trying to discuss this data that we actually clearly haven't analyzed at all, right? And so unless this data is really, really important, if it's so important, then I should have at least spent 15 minutes thinking about it, right? And so if you please don't make a point of saying, here's data that I've not analyzed. All right, so far we've got to through the meat of the talk, and now it's time to actually get to the real conclusions. So we're skin running a little bit low on time, but we'll probably get there okay. And so let me put up, I know I just have a couple of minutes, so we need to leave time for some questions, but let me put up the conclusions here. So MOFs have potential uses as adsorbents for gas separations and capture. Open metal site MOFs show selectivity for olefins over paraffins. Quantum chemistry can be used as a basis for deriving accurate MOF force fields. Force fields have been derived from MOFs with open copper sites. More work is needed before specific MOFs can be recommended for use. Neutron scattering requires expensive facilities, but does give new insight. High-resolution microscopy identifies defects in MOFs in some cases. And finally, watching someone read their conclusions line by line is very boring, okay? So hopefully most of you got down to the bottom of the slide there before I did, but that's my tip. Reading your conclusions line by line is very boring. Please don't do it, and in fact, please don't do it on any of your other slides. It's not a good habit to be in. So we really, truly have nearly reached the conclusion of the talk. I promised that I would be done by 4:30, and so assuming that clock over there is correct, I'm actually running more or less on time in terms of trying to get us out of here and onto the event you came for, which are the refreshments outside. And so now, of course, there's one more thing that you typically have to do with a talk like this, and that is to give some acknowledgements. And so what I've done here is included the acknowledgements to all the different people who've contributed to this work. I particularly wanted to acknowledge all the folks in my group. I actually took this picture of someone else's group because they seemed a lot happier than mine. But you know, the current and recent students and postdocs really have done all the work that I've shown you here, and it would take too much time for me to actually mention them by name, so I'm not going to do that. Of course, it's important also to acknowledge all the places that your ideas came from, and some of the original ideas from this talk came from a conference several years ago, and so I'd like to acknowledge all the folks who were on this Poland, Lithuania, Georgia membrane working group, the photos taken there at a recent meeting of that group. There are a number of other people who contributed. In fact, some of them are in the room. Thank you very much, Kevin. So computational tech support and assistance is always important for keeping our work going. And in fact, some of the original work that went into this research was motivated by a class project a number of years ago. So I want to thank the students who were in CHBE 9417 back in 2012. They decided as a class project to do this conceptual artwork at the end, but that really sort of motivated our thinking about how to think about these different materials. Now, in addition to acknowledging the people, it's incredibly important that we acknowledge the folks who actually gave us the funding. And so let me acknowledge all the organizations that have contributed to funding our work over the years. And so we've had continuous funding from the Department of Energy, particularly this EERE-BS program, very, very important program for our work. We received a small seed grant from the Philippines Department of Energy, who are interested in the sort of renewable energy aspects of what we do. And then the EPA, of course, is quite interested in these kinds of materials, so the EPA has helped us out. We received some early support from the National Energy Technology Lab, and I've listed the different grant numbers here so I can properly acknowledge all of the things they did. I particularly want to highlight the fact that they gave us a supplement in 2012 because we hadn't quite spent all the money that year, and so that was very kind of them. Recently, we've received some NIH funding within this rat survival initiative, and so that's something that I hope will come to fruition, although I haven't really had a great deal of time to talk about it today. And then we actually have a consortium of companies who support our work. So I want to thank these interconnect companies that have helped us out. There's a company who wants to remain nameless, but did ask me to put their logo here. So I put the logo there. Tom's of Maine for their healthcare products. And then Uncle Bob Septic, who were actually instrumental in keeping things working at my summer cabin while the students were working. And so particularly want to thank them. Oh, I can see again my time's running out. I actually had asked Laurie if she would come and help remind me when time is running out, so she's brought down a sample of what our refreshments are going to be outside. So thank you very much, Laurie. It looks delicious, don't you think? I mean, that really looks good. So I'm going to put that over here. Just while we continue the discussion here for a few more minutes. All right, so the point of this slide is if you have a very, very extensive acknowledgement section, it's a really great way to drain away any possible enthusiasm for your work. Okay? In fact, in reality, I would highly recommend you put your acknowledgements at the beginning. It's a perfectly good place to put them. And if you have something that you would like people to remember when they actually come to the end of your talk, then put that on a slide and leave it on the screen. All right, so now we've reached almost the end of the talk. You've already gathered that I'm deliberately continuing well past my allotted time, showing no particular sign that I'm going to end at all. So we're at the stage now where I'm probably 5 minutes past when I should have stopped at the conference. The session chairman or chairwoman is kind of tapping their toes nervously, wondering how they're going to get me off the stage. But I'm just going to stand here because I don't really have anywhere to go, right? And so we're just going to continue to work through these things. But finally, I'll get tired of doing that, and it will be time to take questions and answers. And so at this point, I'm going to pause and see if there happen to be any questions from the audience. Yes, there's one over here. Dr. Walton.
I have a question, a technical question.
Oh, okay, great, great.
From your first conclusion slide.
Okay.
Which was like a long time ago.
Yeah, yeah.
So I think it was propylene selectivity.
Right.
You showed 1 million MOFs, and I just wondered if you could comment on the stability of those.
Oh yeah, sure. That's a great question. And I think, really the best way to think about that question is to think about how these things would work if we put them into a biological system, right? And so that's what we've been doing within this rat initiative, is we've been taking these materials and we've been feeding them to animals. All right, so you get my idea that what I'm trying to do here is I'm not answering your question at all. I've answered the question with a tangent to another topic. I spared you what I really wanted to do, which was to continue for 2 or 3 minutes. You've all seen people do that, right? Answer a question and just talk and talk and talk. But as you can see, we are running a little bit short of time. But I think we've got time for a couple more questions. Are there any more questions from the audience? Yes, Dr. Liu.
I have a very quick question.
Very quick question.
Yes or no?
Okay, yes or no?
Do you think anyone who is a bad presentation giver can learn to do a good presentation?
I think that's actually a very complicated question, and people have debated this for a long time. All right, so that's my second tip for answering questions, which is take a very simple question, give a very long answer, right? Particularly irritating when you've got, remember the cupcake sitting there, it's just waiting for you outside. All right, we probably have time for a couple more questions. Any more questions? Yes, Dr. Kane.
I have a question that it'll take me some time to develop. So it has to do with, you were talking about jargon. And what was occurring to me that jargon in one...
Yeah, that's a great question. I'm really glad that you asked that. All right, so the tip here is don't waste your time listening to the question. I mean, who knows where he was going with that? I want to be able to answer the question that I actually have. All right, so that's my final tip, which is to cut off the questions before it's asked, because that way you can answer the question you want to answer, right? You never know what trouble you might get into if you actually let people finish their question. Now, the problem is, hopefully you've learned something from the presentation this afternoon, but I've given you a lot of tips, right? And not all of you have been taking notes, so that's a little bit disturbing to me. But you've got these 22 tips here, and you really should figure out a way to remember them. So what I decided to do was to develop a handy tool that you can take with you next time you go to a conference. And so you'll be given a copy of this as you leave the room today, and this is a game that I call Bad Talk Bingo. And so what this is a chart where we summarize all the things I did, and you can just check them off as they happen in the talk. And so you'll get, as I said, you'll get a copy as you leave, and you head out for a cupcake this afternoon. I have only one request, and that is when we have our next chemical engineering seminar speaker, you do not stand up in the middle and say, bingo! All right, so that really, truly is the end of the presentation. I will entertain any real questions if there are any, thanks to my colleagues who helped me out there. Are there any burning questions that people have, or has the image of the cupcake just done you in completely? Yeah, down the front.
Are you guys going to start using this during quals?
Yeah, I don't think that would be very kind. All right, well, thank you very much for your attention, and enjoy the rest of your afternoon.